More redox titrations. This time we've got ethane dioic acid crystals that we're making up. Now we can see from the information that when we have them in solution, it's the ethane dioate ions which are oxidized to carbon dioxide by the manganate solution. Well, presumably we know the half equation for the acidified manganate being reduced, but let's put together the half equation for the ethane dioate ions being oxidized. So it's not as difficult as it looks actually. So we've got our ethane dioate ions there, and we're told that they're turning into carbon dioxide, and this balances quite nicely if we just pop a 2 in front of there. And actually all that we're left with now, so there's no hydrogen ions, there's no water involved, so all that we've got left is the charge. So we need 2 electrons on the right hand side to balance the charge. This leaves them reacting in a 2:5 ratio. So we want to multiply the ethane dioate through by 5 and the manganate through by 2. The electrons of course disappearing, so that's going to give us 10 carbon dioxides, and we'll have 2 Mn2 plus and 8 waters. To do the calculation, it probably helps to draw a sketch of the experiment that took place. So there's our ethane dioic acid, which we made up to 250 centimetres cubed, and we took 25 centimetre cubed portions of these ethane dioate ions and reacted them with the manganate, and this required 24.55 centimetres cubed of the acidified manganate for the reaction to be complete. The question is asking us for the concentration of the manganate, so this is where we need to start. We can get the moles of the ethane dioic acid and hence the ethane dioate ions. So the first part is simply the mass over the MR, and that gives us 0.0121 moles, and that's in 250 centimetres cubed. So we know the moles in here, which is, so to get the moles in our conical flask, then we just want 1/10 of that. So that's 1.21 times 10 to the minus 3. Remember, they're reacting in a 2:5 ratio, so 2 moles of manganate for every 5 moles of the ethane dioate ions, which means we want to times by 2 and divide by 5, and that's the moles of the ethane dioate ions that we had before. So we've now got our moles of manganate ions. We just need the concentration of the manganate ions to finish with. So we want the moles divided by the volume, and remember the volume was the average titer, which was 24.55. Divide that by 1,000. So 0.0197 moles per decimetre cubed. In the next example, the difficult part comes really with the half equations. So again, we have our manganate ions, so there's nothing new there, but in the solution we've got 2 things that we're able to oxidize. So we can oxidize iron 2 as well as the ethane dioate ions. So let's start off by looking at how those half equations will work out. So the iron 2 plus ions are oxidised to iron 3+, which gives us 1 electron lost, and the ethane diauate ions will release carbon dioxide when oxidised, and this gives us 2 electrons. Clearly a total of 3. Now let's remind ourselves about the acidified manganate's half equation, which, as we know, has a 5 electron gain. So we're looking at a 3 to 5 ratio in which these are going to react. Let's put that together now. Our overall equation, and we've got this 3 to 5 ratio in which they're reacting. Little sketch of the experiment that was done. So we can see the calculation is going to start by working out the moles of the manganate that reacted, which, using the ratio, will allow us to get the moles of our ions in here, and then we'll scale up to get the moles in here, and we'll have a mass, so we can use the moles and the mass to get the MR, which will allow us to work out X. Okay, let's start with the moles of manganate then. So this is the concentration times the volume. Remember to divide the volume by 1000, and this gives us moles of 5.005 times 10 to the minus 4. So the next thing that we can get is the moles of the iron ethane diauate in 25. Remember that we've got this 5 to 3 ratio, and that gives us 8.34 times 10 to the minus 4. That's in 25, so we want to know what we've got in 250. So we simply need to scale up by a factor of 10. So 8.34 times 10 to the minus 3. We can now get the MR by using the mass and the moles that we worked out in the previous stage. So we're just doing the mass divided by the moles that we've got, and that comes out to be 179.8. So the 179.8 is for the whole of the MR. If we subtract the iron, 2 carbons and 4 oxygens, which is 143.8, that means that our waters are contributing 36 to the MR, which should be fairly reassuring. And if we divide that by 18, which is the MR of one of the waters, then we can see that X is 2. This final example is quite difficult and a little bit different, and it's to do with electrons and reacting ratios. So we're told that we've got this metal Q, and it's in the form of Q2+, and what we're going to do is oxidize Q by using our old friend potassium dichromate 6, and it's acidified. We're also told the concentrations and the volumes of each of them which are reacting, and this means that we're going to be able to work out the moles that we've got of each, and this will enable us to work out the reacting ratio. Let's establish first of all what's happening with the acidified dichromate and its half equation. Well, we're told that the dichromate ends up giving us chromium 3+, so that's the green colour that we've seen before. Remember, we need to balance the chromiums. We then need 7 waters on the right hand side, 14 hydrogen ions, which means we've got a charge of 12+ on the left, 6+ on the right, so we need 6 electrons. Let's now get the moles of the Q 2 plus ions reacting, so that's going to be concentration times volume, and that gives us 3.5 times 10 to the minus 3 moles. For my dichromate, same thing, so 0.04 times 29.2 over 1,000, giving us 1.168 times 10 to the minus 3. So that's the ratio in which they're reacting, which might not jump off the page. So let's divide by the smallest number, and this now does work out quite nicely to show that they are reacting in a 1:3 ratio. Now let's go back to the dichromate half equation. Remember, that took place with an electron gain of 6, and if they're reacting in a 1:3 ratio, that means that each Q2 plus ion must lose 2 electrons when they're reacting. So if we consider the half equation and it's losing 2 electrons, that means the oxidation state of Q will be +4 after the reaction.